So there are 4 traits defined in the Reactive Manifesto. The first one, and the most important one, is that your application should be responsive. Responsive meaning that it should respond in a timely manner to user requests if it is at all possible, like if not all of the servers are dead, right? So this kind of builds user confidence in your system. It provides some quality of service. And then there are 3 other traits which help you realize the responsive trait, right? So if we want to if we want our system to be responsive, we should build it so that it is resilient. Resilient meaning if there's an error, it is properly contained in one component. Data is replicated so that if we lose one replica of data, we can use another one. Errors should be isolated, and components should be able to fail independently without breaking down the whole system. Okay. Another trait is that systems should be elastic. So if we have a sudden increase in the number of users, we should react to that accordingly. So probably increase the resources allocated to our system, scale up our machines, add new hardware, hopefully automatically. But also on the other hand, when the number of users goes down, we should decrease the number of resources consumed. Finally, there's the trait that our applications should be message-driven, and that's the most technical side. Let me just start my timer. So message-driven, the main point here is that the components in our system should communicate asynchronously. Okay, like if they communicate asynchronously, then they probably communicate using some form of messaging. Okay. So when we have a system which is message-driven, which uses messaging between components to provide communication, then there are high hopes that, or higher hopes, let's say, that our components are loosely coupled, that the exact location of each component is transparent to other components, right? So these are all things that are like good to have in a system, and it is kind of easier to do when our system is message-driven. When we have messaging, there are some other things that come into play, like load management, flow control, right? When we have 2 systems exchanging messages, we don't want to drown one system with messages so that it dies because it has to handle too many messages, or it can't fit the messages into memory, right? So we need to somehow control how the messages flow between the components. Here we also have the notion of back pressure. So we want systems which are overloaded to somehow signal the other systems that please stop sending me messages, right? So these are the traits that reactive systems should have. But that's like a bit of, it's a bit of marketing, it's a bit of theory. But let's see how we can actually realize these concepts. So a small note, like in the Reactive Manifesto 1.0, it wasn't message-driven, it was event-driven. So what's the difference here? The difference is that events are very often a business concept, a business domain concept, right? And also, if you have events in your system, it doesn't imply that they are processed asynchronously, right? You can process events synchronously, and that's fine. With messaging, you usually have the asynchronous communication, and that's what the authors of the manifesto wanted to emphasize, that you have the asynchronous communication. OK, so that's the Reactive Manifesto in like 2 minutes. Just a short note about me, so that you know who's talking to. Day to day, I'm a Scala coder for 4 years now. I'm also the co-founder of SoftwareMill. We are a software house spread around Poland, and we do software in Scala and Java. I did a couple of open source projects. They're all very interesting, of course, so you should go check them out all. Plus, I have a blog and Twitter, so that's about it. OK, so to implement the Reactive Manifesto, we are going to use Akka. So if you go to the Akka's website, you can read that it's a toolkit and runtime for building highly concurrent, distributed, resilient, message-driven apps on the JVM, right? So that's exactly what we need, right? It has all the traits enumerated here.
Coincidence?
Yeah, not really, no. So like the core Akka, the core of Akka contains an implementation of lightweight actors. Actors are entities which encapsulate some possibly mutable state. And we have a guarantee. Actors, basically, the only way for an actor to communicate with the outside world is by exchanging messages. So we have the asynchronous message passing right out of the box, right? So the only way to communicate is using messages. And we have a guarantee that each actor processes at most one message at a time. So the state that is encapsulated by an actor is protected from any concurrent access, right? So that's like the basis of actors. But Akka is much more. There's like a lot of other modules, some of them like in various degree of experientiality, let's say. So there's the remoting module. It's not experimental, so we are not going to talk about it. In the remoting module, we can connect actors which live on different nodes over the network. On top of that, there's the clustering module, which we are going to use. It provides cluster membership, so Akka nodes on which Akka runs can form a cluster, and they maintain a uniform cluster view. Then we have persistence. That's a module which is experimental but close to being released, I think. And using persistence, you can implement things like event sourcing. You can persist the state of an actor into journals, either on disk or in a database like Cassandra. Then there's Acta Streams, which is the newest addition to the family. It's used for defining data processing pipelines with built-in back pressure. We are going to use that one as well. And finally, there's Akka HTTP, which is the rebranded Spray.io, if you know Spray. It's a DSL for building REST endpoints. It's a very nice DSL. Plus, it's an implementation of the lower level of actually parsing all the establishing HTTP connections, parsing all the headers, and so on. OK, so that's like an overview of Akka. Are you with me, more or less? More or less. OK. So what are we going to do? So we are going to build a very simple application. The application is going to process some data. So I have flight data from the US from 2008. And it's like all the takeoffs and the landings from US airports. It's about like a couple hundred megs of data. So it's not something you process in a second, but also not like big data. Not like reasonable for a demo, I hope. So we have like all the takeoff and landings. And what we want to calculate is we want to look at flights. So there's like, you can see that there's a lot of data about each flight here, right? You can see that there's a lot of fields. So among other data, we have the origin airport, the destination airport, distance between the airports, and the delay. And we want to see what is the flight which had the biggest delay per mile flown. So like the proportionally biggest delay, okay? So we are going to have a server which will calculate that biggest delay. And it will calculate based on data received from remote clients which connect to the server over TCP and stream the CSV file, stream the data to the server. Okay? And the server will keep track of what's the current worst flight to be on if you want to have, like, when comparing the delay per mile. OK, so that's like the input file. Of course, it's like 10 lines. I'm not going to open a 500 meg file in IntelliJ. Even though it's a great IDE, it's not that great. OK, so that's like what we are going to parse. So I have the model ready, because it's not very interesting. So we have like a flight data case class, right, which has the basic data from to distance miles, delay minutes. I have a way of, if I have a parsed line, a CSV line, right, that's the parsed CSV line. I can turn it into a flight data if it contains the fields I'm interested in. And then we have a class which actually calculates from a flight data what is the delay per mile. Okay, so that's that's the calculation over here. It's a simple division, so not very complicated. If there's no delay, we get a none here. So that we are going to use that throughout the demo. OK, so let's start writing some code. I will start with the server. So that's going to be our server, the receiver. So the receiver is going to need some stuff. It's going to need the address on which we are going to listen for client connections. Okay, it's going to be a socket address, and it's going to need an implicit actor system, so that we can create some actors for processing the data. Okay, we need a method to actually run the thing. Okay, so what we will do now is we want to bind to the socket, to the address, right? We want to listen on to client connections, and we want to receive a stream of data from the clients, okay? But we don't want to just receive any stream. We want to receive a reactive stream of data. Now, what is a reactive stream? It's actually quite a simple thing. A reactive stream is like a data processing pipeline, okay? In a pipeline, we have a number of stages. Each stage does something to the data, okay? And it is reactive because data doesn't flow like as it is available. It only flows on demand, right? So if the component number 10 decides that it wants data, it signals demand to the previous components. And the previous components then signal demand to the previous components and all the way to the data source. And the data source spits out data only when there is actually demand for the data, okay? And it does so not one by one, but it can do like small batches of data. So I can say I want 100 elements. So the data then will travel in batches of up to 100 elements, okay? So each such a stream has three basic components. There's a data source, which has no inputs and one output of data of a given type. There's a sink, which has one input and no outputs, okay? And there's a flow, which has exactly one input and one output, right? And to create a stream, we, of course, need a source, any number of flow elements in the middle, and a sink, okay? So I guess that's quite reasonable. OK, so what we are going to do is we want to stream over TCP. So we are going to use the stream TCP extension from Akka Streams. So that is going to create us a TCP stream of data coming from TCP, right, in a reactive way. So we are only going to read from the socket when there's actual demand. Okay, when there's no demand, the socket buffers will fill up, and if the other side is reactive as well, the other side will stop sending data. So we have the stream TCP. We bind to the address given. If the other side is not reactive and it keeps writing to the socket, eventually it will out of memory, right? If it reads from a file and tries to write on the socket, but the socket buffer is full, so the socket will stop accepting in more data, and it will accumulate the data in memory and run out of memory. Same here, right? If any component is not reactive and we block somewhere downstream, we risk an out of memory. And here, if we have the explicit demand passed, we don't run into such risks. OK, so we bind our stream TCP extension, and we get a stream of connections. Again, that's a reactive stream. Of no data yet. So far, we only have a reactive stream of connections. Why is it reactive? Well, if our server is overloaded, we don't want to accept new connections as well, right? We only want to accept new connections when there's actual computing power to serve those requests. Okay? So we want that component to be back pressured as well. Okay? So now for each connection, we are going to take a connection here. OK, we are going just to print line that we bound to that address, bound to address. OK, so now we have a connection, and from the connection we can obtain a flow. A flow is like the middle part of the stream, right? And it represents the client flow, right? The client, if we you normally think of a flow like from input to output. Here we have to think the other way. If we receive something from the client, we usually need to give something back, right? The client sends us some data, a request, and we respond with some data. Okay? So we take that flow, That's a flow from bytes to bytes. A byte string is like a beta byte array. So the client spits out bytes. Okay. So what the first thing we need to do is we want to transform that into actual strings, because we have raw bytes. So we add a transform stage to our pipeline, parse lines stage, and we add a stage which will actually parse the bytes into lines. That's some buffer. Okay, so now we have a stream which spits out strings, okay, delimited by new lines. So once we have those strings, we can now filter out anything that doesn't start with 20, because there are some headers here which we want to skip, right? We only want the raw data, right? So we filter out any strings that do not start with 20. Then we transform that strings into byte arrays, right? So we do a simple map. On the streams, we have like a lot of operations that you probably know from Scala collections. So we take each string and we split it by commas, so we get an array of strings. Now we can use our map concat. We can use our model that we have prepared earlier, right? So we create our data class, which represents a single flight. So this returns an option, because the data can be incorrect still. So we turn the option into a list. That list is going to have 0, 1 elements. And there is no flat map in streams, but instead, there is a map concat. So it's not, the name is different because it's not like a monadic flat map, or it is just a map which concats all the elements of the given list, okay? But it behaves a bit like a flat map. Right, so for some elements we are going to have no flight data. For some we are going to have 1. Okay, so we have a stream which outputs flight data right now, right? So, but we still have a flow, right? We don't have a complete stream. We need a sink. So let's provide a sink. For now, we are just going to do a for each sink. So for each flight data received, we are going to print line that flight data, and we are going to pretend that we are really slow in processing the data. So we are going to do a thread sleep for now. Okay, so that's our flow. That's our sink, sorry. Why is it a sink? Okay, so here we have a sink, right? So we have the end of the stream. That's the sink. That's the flow, right? So if you connect a flow to a sink, we get something which has 1 input and no outputs. So that's a sink, right? So, okay, so we have the sink. We need the source. So we need to somehow respond to the client. Here we never send any response to the client. We just accept data and process it. So we are going to use a lazy empty source. So that's a source which has no elements. We are going to connect it to our receive sink. Okay, and now we have a full data processing pipeline. Actually, if we do that, there's no data is going to be processed just yet, because what we have is just like a blueprint, a description of how we want to process the data. We still have to run it. And to run it, we have to somehow materialize this description of our data processing pipeline, right? We have a number of steps here. Like we have a transform step, we have a filter step, we have a map step, but that's only like a description of how our pipeline looks. We have to materialize it so that the actual data processing starts, okay? So we have to do run, okay? And when we do run, things are actually going to start being processed. Now, run has an implicit argument, which is a flow materializer, which we have to provide. Actor flow materializer. And there is currently one default implementation of a flow materializer, and it's actor-based. So this flow materializer is being used over here when we actually, using our blueprint, when we actually run the stream, okay? And this, of course, is going to use actors, like each stage, like this over here, is going to be mapped to an actor, and the actor is going to do the actual work, okay? And it's all going to be back pressured. So since we are slowly processing data here, data from the socket will be read only when there is like sufficient demand in the whole in the whole stream, right? So we are going to read from the socket twice every second, in effect. The materializer is also used here. That's like a shortcut, because here we have a stream of of connections, right? And here we have like a so here we create a for each sync and a run in one method. Okay, so that's just a shortcut method, but it uses the same mechanism of materializing the streams. Okay, so so that's the receiver part. Let me just write an app which I can actually run. Receiver extends up. Implicit val system. We create a new actor system so that we can actually create actors. New receiver. New. We need to provide the address, localhost 2182. .run. Okay, so let's run our server. Hopefully it will run. Okay, it's running. Now we need the client. We don't have time to write the client from scratch, but it is like the same principle over here. In the client, we create a source which reads data from a file. Okay, and then we connect that source. So we don't do a bind. We do an outgoing connection here. Okay, so we connect to the server in the client, but like all the concepts are the same as in the server, right? So we read data from a file. It is read in a reactive way, so we only read from the file when there is demand, and that demand flows all the way from our sink through the TCP connection, through these processing stages in the client to the source that is in the client. Okay, so let's try running our client and let's see if the server receives anything over here. Yeah, we are receiving some data. Okay, we are receiving it one every half second, and the sender didn't out of memory, so even though the file is huge, it didn't get read into memory all at once, though you can't see it really here. Okay, so that's our first step. So now we will continue to actually doing something more interesting with the data. Yeah. Mm-hmm. Well, you don't see it, but if you are using the actor flow materializer, yeah, it's going to be mapped to an actor, which will concurrently, probably with the other stages, process the data. Yeah. Okay, so now we have the receiver. Let's create an actor which will process our data and actually calculate the biggest delay. Okay, largest delay actor. Okay, so we are going to have an actor, right? Now we want our actor to be reactive aware. So we want our actor, like normally when you send messages to an actor, it doesn't signal any demand, give me more, I have enough, right? We need to make our actor somehow aware of the fact that we are in a reactive system. So we need our actor to produce demand to give me more messages, right? So we are going to mix in the actor subscriber trait. Okay. Okay. So we will have a variable. That's our protected internal actor state. Largest delay, which is going to be an option flight with delay per mile. Initially, we don't have any data, so it's none. And we have a receive method, which we are going to use to receive, right? That's the method which is invoked when an actor receives a message. Right? So now when we receive a new flight data, okay, so the on next is a wrapper, not the def here. The on case. Yeah, the on next is a wrapper which is provided by the actor subscriber. So that's like if we send a normal flight data to our actor, if we have the actor subscriber mixed in, our data is going to be wrapped into an on next, right? On next data element that is coming from the reactive stream. Okay, so when we get new data, we calculate the biggest delay. So that's our data. So if the flight was delayed at all, so that's why we do the for each, we are going to process the delay data, and the processing is going to be quite simple. Well, no. Now idea is trying to be too smart. The processing is going to be quite simple. So we are going to update our largest delay to be some we are just going to take the maximum. So our data class implements a comparable interface, so it can take the maximum. Okay, so we just take the maximum out of 1 or 2 elements from a list. So nothing complicated here. So we have a method which actually updates our internal actor state. Okay, so still we need to somehow provide the notion of how much elements are we currently processing and how much elements we want to signal demand for. Okay, so to do that, we need to provide an implementation of a request strategy. So that's a thing from the actor subscriber. So here we will use the maximum in-flight request strategy. Yeah. Okay. So let's say that we want to specify that we can only handle at most 10 messages at a time. Okay. We are going to have an internal counter of how many messages we are currently processing. So here, so far, the processing is very simple, right? Because we only update our internal counter. So this really doesn't make sense just yet, but wait a second. So you know, processing a message in an actor can be anything from updating state to actually communicating with an external system, right? So if it is communicating with an external system, for example, so this in-flight counter can be non-zero quite often, right? So this means how many requests, how many messages are like in the process of being still well processed, right? So far we have very simple processing. So we are just incrementing and decrementing our counter. Effectively, we are not doing anything special. Okay, but let's leave it at that for now. And now we can connect our largest delay actor. We need to connect it to our data processing pipeline. So let's go back to our receiver, and we are going to substitute the sink. So let's create an instance of our actor. Largest delay actor is going to be system actor of props. Largest delay actor. Yeah. Okay. Import that. Okay. So we just create an Akka actor, right? Of that class. That's our actor. So instead of a for each sink, we are going to send data to a sink, which is an actor. Subscriber. We need to explicitly specify what kind of data it accepts because actors are untyped, at least as for now. So we are creating a sink which sends data to an actor. Okay, and that actor is what we have created over here. Okay. Okay. One more thing, so that we can actually see, what kind of data, like what's the current state of the processing. Each second, we are going to send a message to the actor. Please log what's the current largest delay. System scheduler schedule 0 seconds every second. Send to the largest delay actor a message log largest delay. Okay. We need to import two things. We need to import the dispatcher, so that we can actually do that, and we need to import that nice syntax over here, 0.seconds. So we import that syntax, import Scala concurrent duration. Okay, and in our actor we need to handle the log largest delay message, and we are just going to print line largest delay so far, largest delay, so that we know what's happening. Okay, so yeah. So
can we check much the normal messages that you also now practice?
Yes, yes. So here, like the flight data, it goes through the actor subscriber. So it goes through the sync decoration, right? So that is when it's being enriched with the on next, right? So that here we know that it's coming from the reactive stream, and here is just a normal message, you know, once per second. So it's not being back pressured or anything. No, why? Like here we can do any pattern matching, right? So whatever our stream is producing, we can. Yeah, you need to have some common type. Yes, yes. It can be an either, maybe for example. Okay, so let's try running that. So first we run the server, and then we try right, so we have no clients connected, right? So we have no largest delay computed. Now we run the sender. Okay, so the sender sends some data. We have a new client connected, and we can see that there are some flights coming in, and there are some flights which had like 522 seconds delay per mile. So that's very bad, but it happens as you can see. Okay, so that works luckily. So okay, so we have a system which is like we have the back pressure from the actor which consumes the data all the way to the client which produces the data, reads from disk over the network, right? So it is a bit reactive, but still like the server might crash, and if it crashes, we lose all the data. So that's bad, right? So let's do something about it. Okay, so yeah, nothing here. So now we are going to use Akka persistence to actually store the state that we are computing in our actor. Okay, so here we have some state which we are computing as the data comes in, and we want to persist that state so that it is safe from crashes. So instead of actor, we are going to extend persistent actor. Okay, persistent actor, yeah. So we need to provide a persistence ID, which is like a key in a database, using which the state of our actor is going to be stored. So anything, any string, as long as it's unique, will work. Okay, so now when we actually receive, we need to implement receive command. That's a minor thing. Okay, so what do we know? Now, when we receive data, before we process it, we are going to save it. So we are going to save an event. Like it behaves a bit like an event source system. So we are saving events. Okay, so we received an event. We have the flight with delay per mile. We are going to save it into our journal. So we call persist async on the data received, right? And only once that data is persisted, we are going to actually process the data and decrement the in-flight counter, okay? And now the in-flight counter makes a bit more sense, right? Because it may happen that the disk is busy, and it's going to accumulate 10 pending writes, right, of the data, and like not complete them for I don't know, 2 seconds or so. And during that time, like the actor will stop generating demand, right? And the data will stop flowing, because here we cannot process any more data, right? Because the disk does something else, right? So here, like quite often, the in-flight counter is going to be non-zero, because we're only decrementing it once the data is truly processed, meaning here, at least it means that it is written to our journal. Okay, so that's like the writing case. Now, what about reading data? So it sometimes happens that our actor crashes. So when it starts up, it's going to have its state restored from whatever is written to the disk, and then we will have the receive recover called. Okay. And here we are only going to receive the events that we've actually written. We have written events of this type, right? Because here we write D. So that's of this type. So if D is of type flight with delay per mile, we are just updating the internal state with that event, right? The events are going to be replayed in order as they were persisted. So we are going to end up with the same state as if we received them all like from the stream. Okay? So by default, there's no journal here yet. So by default, this is going to be written on disk. There's like a default journal implementation which uses level DB, I think. But you can easily swap the journals, and you can use, for example, Cassandra, which is a replicated database, and then your data is safe, like replicated all over the world and so on. Well, you have to. OK, so let's try actually running that, and let's see if it works. So let's run the server. The server shouldn't have any data, right? No data yet. We run the client, which streams the data. So yeah, we have some data streamed from the client. Now our receiver crashes. OK, and yeah, we can stop the sender as well. Now let's restart the receiver. and let's see if it has any data or not. Yeah, it has some data, right? So it recovered the data properly. Okay, so so that's persistence, which we can use to save the state. Okay, and one thing that is left, I don't have, of course, a lot of time left. So now we are safe against crashes of a single server, right? But still, like, if the server restarts, we are safe. But if it doesn't restart, we are not safe. Like, we have lost our functionality. We are not responsive anymore, right? So the question, of course, here is that we need a cluster of these things running on different machines. And when one dies, we want the others to take over. So I'm not going to code everything here because we are running out of time. So I'm just going to copy a bit of code and explain what it does. Sorry for that. OK, so to create a cluster in Akka, it's like not a lot of code. That's all the code we need to actually create the cluster. OK? So the first thing you need is you need to provide alternative configuration. That's the configuration. The main points of the configuration is that we are using a clustered actor provider. Okay, so that's one thing in the configuration. And we need to provide some seed nodes. So how the cluster should look for initial members. Okay, so that they find each other. So we are going to run 3 nodes on one machine here, and they have different ports, 1, 2, 3, right? Okay, so that's like the basic, the minimum configuration you actually need to run a cluster. So what we want to do here is we want to form a cluster of 3 machines, and on that cluster we want to have exactly one of that machines running our receiver server. Okay, and that exactly one server is going to accept connections from client, and then they will be able to stream data to that server. So what we need is we need a cluster Singleton. Okay, so there's an Akka module for that. It's called the cluster Singleton manager over here. So on each member of the cluster, we start a cluster Singleton manager, and that manager makes sure that it will run the provided actor. So here's the provided actor. It will run the provided actor. It will start the provided actor on exactly one node in the cluster. Okay. Okay. So once again, here we have the configuration, right, which I have shown you with the cluster actor provider. We override the configuration with our port, right, because we need to specify what port to bind on the cluster communication. Here we start the cluster using the configuration, right? We use the cluster configuration. The cluster is formed. Then we start a cluster Singleton manager, which is going to run the provided actor on exactly one node. Okay, and that actor, so that actor is implemented over here. So what it does only one thing. In fact, when it starts, it runs our receiver. Okay, so that receiver is exactly the same code, no modifications, as we have written before. Okay, so we have an actor which starts our receiver server, and that receiver binds on some port and accepts connections from clients. Okay, so let's create 3 nodes. Clustered receiver 1 extends up. Okay, new receiver cluster node, and we're going to use port 9171. Sorry, we're going to run it. So we are using 2 ports here. One is the port for cluster communication, right? So all 3 nodes are going to bind on 3 different ports for cluster communication, and another port is where our server actually listens for client connections. And it's going to be that plus 10, right? So here we do the plus 10. Okay. So let's create 3 of those. Okay. So I have 3 nodes. I will just remove whatever state is stored currently in the actor so that we have a clean system. I remove the journal. So that's like the Akka persistence thing from the previous examples. Okay. So let's run these 3 cluster nodes. Okay. And yeah, I do need to start them on different ports. Thank you. So 2 and 3. 1, 2, and 3. Okay, so it's going to take a couple of seconds to actually form the cluster, But we should see that on exactly one node should start reporting that it doesn't have any largest delay yet, right? So no cluster yet. What is it actually doing? That's the younger node. Oh, here we have it, right? So on the first node, we have information that we have no data yet. So now let's stream some data to that to node number 1, right? So I will just change the port here so it connects to the right port. Okay, we start the sender. It streams some data. Yeah, we have some data here on the first node, right? Okay, so now what? Now we, of course, kill the first node, right? What else can we do? So let's kill it. And hopefully, now the data will be, because the journal is shared across, because it's on my machine, right? The journal is shared. So the data should be recovered on another node. So let's see, number 2, nothing yet. That's like a 10-second window through in which they try to detect if the node is really dead or not. And yeah, on node number 2, we have the data recovered as we wanted to. Okay. So that's clustering. And yeah, I have 1 minute left, so that's a good timing. So just to sum up, I have 4 more slides for the end. And let's start with right. So we have implemented at least part of the Reactive Manifesto, right? We have a responsive system. We have provided resiliency through clustering and persistence. We have provided elasticity, so we react to varying component loads using back pressure and Akka Streams. And everything is message-driven thanks to actor communication. There's a couple of things you could do more here, right? You could discover on which node our server is actually running to adjust the port and the address. And you can do that with a cluster client that's also provided by Akka. We should also provide some reconnect behavior on the client. So when the one server dies, the client should try to reconnect to another server. And we could also use snapshots and persistence so that we don't always recover, so that we don't always read all data from the beginning of time when we recover actor state. So there's like a bit more that we could do to actually enhance that system, but that's not enough for 4 to 5 minutes. So if you're interested in that stuff, this code for that presentation is on GitHub. If you would like to see a bit more complete version, like a reactive message queue written in a very similar way, but with the enhancements I showed on the previous slides, is also on GitHub. The reactive streams is like a broader initiative. Akka is only one implementation of the reactive streams standard. There are also others, and they hopefully interoperate. Well, they should interoperate. That's the idea, but we'll see how it is in the reality. And I have one last invitation. So I have stickers as well. I'm proud of my code stickers, and I have Scala Time stickers. If you're interested in Scala, Scala Time is our newsletter. And also, there's going to be a free to attend one-day conference in Warsaw on the 11th of April. So if you would like to come, feel invited. It's on a Saturday. There's a party afterwards. So yeah, sign up for the newsletter. We are going to start registration soon. And if you have any questions, I'm not sure if we have any time, but yeah, sure. What's the advantage of using just Akka instead of Spark? So with Akka, so Spark is built on top of Akka, right? It's not built on top of Akka Streams. So I'm not sure how back pressure looks in Spark. But here you have like it is maybe a bit lower level, but also you can you have more elasticity in what you can actually do, right? You have well, if you have just a data processing pipeline, then maybe Spark will be better. If you have a data processing pipeline which needs to connect to some other systems, provide some persistence, provide some failover clustering, so maybe Akka is a better choice then. Yeah.
Might be a few messages lost, right? Then they are not persistent in disk yet, and they are still in the queue and so on.
Yes, messages here in that example could be lost. Yes, yes, that's true. That's true. That we didn't we didn't build any like message acknowledgements, right? So and it's not provided out of the box as well. Yeah. Yeah. Unit testing for? Unit testing for resilience. Well, testing is a very good question. There is a testing framework, so you could test actors in many ways. There is an Akka test kit, and I guess you could build a testing for like some testing infrastructure around that, and you could also start a cluster in your tests, just as we did here. But I don't think that's like anything specifically in Akka for testing resilience. But I think using test kit and like the fact that you can run multiple nodes quite easily, right? That shouldn't be a big problem. Yeah. Oh, that's good. Thanks. Yeah.
So when you create a cluster of actors and, for example, you want to implement a sharding, so like, is it possible to do the cluster?
Yeah, there's an extension also, like Singleton. There's a sharding extension, so you can have like so the typical use case, I guess, or the first use case was to implement aggregate roots, which are present on different nodes. Like each aggregate root has some node on which it lives, and yeah, so there's an extension you can implement sharding with it as well. Okay, thanks a lot. I'm here for like the next to the end of the conference. Thanks.